Good afternoon, everyone. Uh, so I'm going to talk about Pig on Storm and the thing called hybrid mode. So before we dive in, just wanted to call out that Pig on Storm is not an open source project yet, and we are working on performance testing for this for past 3 months, and also coding for what is known as a hybrid mode. So I'm going to cover Pig and Storm, and then Pig on Storm, and what we call as the hybrid mode. So let's just dive in. So most of you know Pig. Pig is a higher-level language for expressing your MapReduce logic. So here you have a bunch of sentences which you load from HDFS into a relation, and those sentences you tokenize them and make words out of them, and then you group similar words together, and then you do a count of those words, right? So this is a simple word counting example in Pig. The same thing can be done in Storm using what is known as a Storm topology. So how many people have worked with Storm here? Okay. So I'm going to cover Storm anyway. So Storm is a real-time stream processing platform which uses a DAG of spouts and bolts. The spouts that you see in rectangle and the bolts you see in circle, those are the processing units. It uses a DAG of spouts and bolts to actually give you the execution for whatever kind of logic you want. So here you see the same thing. You have the same sentences coming in, and the Kafka loader, you get the sentences from a data queue, and Kafka loader loads this particular data, and then sends it to the tokenizer bolts, which basically takes each of these sentences and then splits them into words. Then you do a group by of those words, and then you do a count of those words, right? So very simple. So it's the same word count example, which you see in Storm again. Right, very simple to implement. So Pig on Storm basically is nothing but putting these things together. So you write your script in Pig, and it gets converted into Storm topology automatically, right? So as you can see here, there is a one-on-one correspondence, almost a one-on-one correspondence between each of the Pig statements and the Storm constructs, right? So let's go in more details. So before going into Pig on Storm further, just wanted to cover some basics of Storm. There are two modes of Storm, one of which is very important for Pig on Storm, and it's not widely known. So I would like to cover both of them, so some parts of Storm here. So the first mode is called the event processing mode, which is very popular. In fact, most of you must have used this mode of Storm more than anything else. So you get the event data stream one step at a time into the spout. The spout acquires it and sends it to each of the bolts, right, for processing. So this is your DAG. Now, this is one of the most popular modes in Storm. The other mode, which is slightly more advanced in Storm, is called the batch processing mode, where you take a bunch of events, tag it with a batch ID, and then send the whole batch for processing inside Storm. And then you track this whole batch as a single unit, right? So batch processing mode is used in topologies which require high throughput, and in many advanced cases, it comes in pretty handy. Now, this is the mode which was available in Storm in something called transactional topologies, and since then it has been subsumed by a platform called Trident, which sits on top of Storm. So this is Trident is a language which sits on top of Storm, and batch processing is available only via Trident now in Storm. So since this is very important for Pig on Storm, just let's do some deep dive here, just 2-3 slides here. So in case of batch processing mode, the spout becomes much more complicated. Spout is the place which acquires the data from data sources. So you have a unit called coordinator, which generates a batch ID periodically. So you have batch ID 1 being generated by the spout here at time t1, and maybe every minute a separate batch ID is generated. So here you see the batch ID 1 is sent to emitters. Emitters can be considered as threads which go and acquire the data from external data sources like Kafka and AMQ. And once for every batch, right? So here you see that there are different tuples which are coming in from Kafka and AMQ acquired by the emitter threads for that particular batch, which is batch ID 1. Now, this is kind of, so one of the things to note here is that you do not buffer all the data inside this particular spout for that particular batch before sending it to the topology. What you do here is, as and when the data arrives, you mark the data. So when tuple 1 arrives, it is tagged with the current batch ID, which is batch ID 1, and sent to the topology. Similarly, you have the second data point, tuple 2, which again comes in, and you mark it with the current batch ID, which is batch ID 1, and again send it down the topology, right? Now, so you can see here that Storm achieves pipelining and efficiency within a batch by doing this kind of thing, right? So you have multiple tuples being processed at the same time, as and when they come in. You do not wait for the whole batch to buffer in the spout, right? So this is pipelining inside a batch in Storm. So after some time, the second batch starts, so batch ID 2 starts. And again, the same thing starts. Again, you get the data for the second batch. Now, one of the important things to note here is the first batch is being processed in red, and the second batch has already started. So this is the way Storm achieves pipelining across batches. So you have pipelining inside a batch, and you have pipelining across batches in Storm, which gives it the efficiency in parallelism, right? So parallelism is actually achieved by having multiple boards, but you have pipelining between batches, right? If you want any kind of ordering between these batches while processing, you can use committers in Storm, but I'm not going to get into the details of that. Committers can be used at any point in the topology, at any board, right? Okay, so with that much background, let's get into Pig on Storm. Let's get to real content of the talk here. So there are 4 aspects which I would like to cover here. The first one is very simple and very obvious, that you write a Pig script and it runs on both Storm and MapReduce, both the platforms, with minimal to no changes at all, right? Now, you think in terms of Pig, you write your UDFs in Pig. If you're a Pig developer, you don't have to understand Storm much. You just write everything in Pig and everything will work seamlessly on Storm. Now, this was pretty much a no-brainer for us because most of our modules and applications were written in MR, for MR was written in Pig. And we wanted to seamlessly integrate those and migrate those over to Storm. So this was kind of pretty obvious for us, a choice for us, that you just have Pig and everything works on both the platforms. The second aspect is called batch aggregation. So you can do aggregation inside a batch, within a batch, and you can do aggregation of data across batches in Storm now with Pig on Storm. And this is expressible via Pig now, right? So aggregation across batches is slightly difficult to do in native Storm, and this allows you to do that, right? The third aspect is rich state semantics. So neither Pig nor Storm takes any kind of a position on state or store. It is purely left to the developer to figure out his or her own constructs and develop those from scratch as and when it is needed. And it's difficult to get, actually, right? Because you need state and you need store all the time. And neither Pig nor Storm takes any kind of position on that. So with Pig on Storm now, there are certain state semantics which are available out of the box. And 2 of them I would like to share here, and there are some more upcoming. One is called global mutable state. So you read in a state from a store, and you mutate that particular state and push it back. The second one, and this is part of the thing which is available in Pig. You can express it via Pig. The second one is called sliding windows. So sliding windows is pretty interesting. It's used in a lot of applications, and we'll look into a real-world example here. But at a very high level, sliding window is a window of data in memory, and it consists of fixed number of Storm batches, right? And every minute, this sliding window moves. So you get a new batch added, and the oldest batch gets deleted. So we'll look into this in more detail. And the fourth aspect is the hybrid mode. So hybrid mode is something which we are working. This is something very new. And we'll look into this also as a separate part of the presentation. But at a very high level, you write your Pig script and just submit it to our system. And the system figures out what should run on Storm, which parts of the script should run on MapReduce. And it sets up the data exchange mechanisms between the 2 automatically, all right? And the data exchange can happen at the granularity of a Pig relation. So you just write your Pig script, and what should go on where is automatically figured out. Okay, and that's the mode which we are right now working on. Okay, so it's important to get your head around thinking streaming in Pig. So it's kind of difficult for people who generally work with batch processing in MapReduce to think, how does Pig work for Storm, right? So what you see here is a Pig script, but what I see is a Storm topology which is running infinitely here. So in conventional Pig, you load the data from a HDFS store and push it into a relation. In Pig on Storm, you load the data from a messaging queue and push it into a relation. And you can consider that relation, Pig relation like A, as an open-ended pipe which keeps getting data from the data sources continuously. Now, the right granularity to think here is in terms of storm batches. So you should think in terms of storm batches which are flowing down in this particular topology. And you can do aggregation within a batch, and you can do aggregation across batches, across the storm batches. Now, and we already saw that you can do pipelining within a batch, and you have pipelining across batches in Storm automatically, right? So for efficiency reasons. I would like to cover actually a real-world example where we took our trending module, trending application, and ported it onto Storm from our classic pipeline, which is just a bunch of scripts. And ultimately, we ported it to Pig on Storm. So it's not important to understand the algorithm here in detail, but I would still go through some of the things so that you appreciate the implication of the problem on the underlying platform with respect to performance and scale, and also the algorithmic needs of that particular problem, right? So let's say you have a query called Obama means elections coming to you right now, currently, let's say it's 4 o'clock, whatever, right? And this query could be coming from a search stream, Twitter stream, or wherever it is. And you want to find out if this particular query is trending or not. So what you do is you pass this particular query through the two sliding windows, current sliding window and past sliding window. And then you calculate the probability of this query in both those windows. This is a standard machine learning language model stuff, so I'm not going to get into the details of that. Now, once you have found the probability of this query in these two windows, you take a ratio of the two, and then see if this ratio is above a particular threshold. If the ratio is above a particular threshold, you say that the query is trending. This is the basic algorithm, right? So what is this sliding window, and what does it do? So let's take the example of the current sliding window. So the current sliding window consists of the data which the system has seen in past 4 hours. So if it is 4 o'clock right now, the system will see, the sliding window will have the data from 12 o'clock to 4 o'clock, right? And of all the queries that the system has seen. And this particular data is divided into 1-minute storm batches, right? So in a 4-hour sliding window, you have roughly 240 storm batches, which will be maintained in the sliding window. And every minute, this particular sliding window moves. So a new batch gets added, and the oldest batch gets deleted, all right? And every minute, the processing need is that we calculate the frequency of n-grams and the total count of the n-grams and the unique vocabulary count in this particular sliding window, all right? The same thing which we do for the past window. I have shown here only one past window, but you can have multiple past windows, like past window for yesterday, week before, and maybe a month before. So the point to drive home here is that the implication of this particular problem on the underlying platform, both in terms of scale and efficiency, as well as the need for out-of-the-box data structures is pretty high. And Storm does not give those things by default, right? And you also have to construct all these things from scratch. So when we did this particular algorithm and we implemented it, the topology looks something like this. And it took around 5,000 lines of code in Storm, native Storm, because nothing is available out of the box. You have to develop all these constructs by yourself, the constructs of sliding windows and stuff like that, right? When we did this in Pig on Storm, it took around a couple of 100 lines of code just because of the fact that Pig on Storm is very expressible. Pig is expressible, that is one. The second thing is that we provided a lot of out-of-the-box constructs like sliding windows, state management, semantics, and stuff like that. So with that, our older pipeline, or the classic pipeline, used to generate trends once every 55 minutes. And our latest pipelines in Storm generated it once every 5 minutes. So we beat our nearest competitors here by around 8 to 10 times with respect to trend latency. And of course, we have fresher and better trends. So this is how the code looks like, but I'm not going to get into the details of this. I just want to cover some 2-3 statements here just to show you how it works. This is Pig on Storm, basically. The syntax is pretty much like Pig. So in fact, Pig. We maintain the sanctity in terms of syntax and semantics for Pig, right? So the way you think, the way you code, you just code in terms of Pig. But a topology gets formed, and this forms like this. So you get the data from search or Twitter through a Kafka spout. So you see the Kafka emitter here, which is loading the data from search or Twitter. I'm just taking an illustrative example. Internally, we do not use Kafka, but I'm just showing an example here. So that particular data is loaded into a relation called live queries, which is a batch of tuples. And then you produce a new relation called n-grams, which is basically a stream in Storm. And that data for the current batch, which may be a 1-minute batch, let's say, would be written into HBase, and the batch number 8 that you see in green here is written in HBase. The n-grams are written in HBase. The second part of the topology consists of reading this last 6 batches as given in this particular code, the third line here. Last 6 batches with respect to the current batch into a sliding window which we want, right, and produce a new relation called n-gram models. So now you have n-grams and you have n-gram models, and you join them in a bolt. So the last statement says join these two, relations in Pig, which are streams in Storm, through a bolt and write it to a separate table in HBase. Now, so what's happening here at a very high level is, on the right-hand side, you have the live queries coming in for which you want to find out the probability of each of the n-grams, as I told you in the last slide. You want to calculate the probability of this query so as to find whether it is trending or not. On the left-hand side, you have a sliding window of older batches, which forms your language model. In the CW1 bolt, you join the streams, both these streams, to calculate the counts for an n-gram for each of the queries, unique vocab counts, etc., and using the n-gram model as the language model for your problem, right? So, of course, people who have worked in Pig find it, it takes time to get through this particular thinking, right? How does relations turn out into streams and stuff like that? But if you go through this enough, I think you will get the point that each of the relations are equivalent to streams and Storm and stuff like that. Although when you code in Pig on Storm, you don't have to really necessarily understand Storm that much. Okay, so in summary, what we provide here is efficient in-memory state, right, through Pig on Storm. We provide rich out-of-the-box in-memory data structures, union, intersections, sketches, etc. The reason being, these are very important and used in many applications, and this is not available by default in Storm. We provide advanced semantics for state, like sliding windows, and rich expression of state via Pig. So Pig also gets enhanced that way, right? Because you provide all these kind of things. Now, of course, we provide fast recovery of in-memory. So we plan to provide actually fast recovery of in-memory states, which we maintain in these bolts in Storm. And we also potentially want to have queryable states going forward. So this is all in the plan, basically. But till this slide, we have implemented most of it, and I was just showing you topology, written in Pig and working on Storm. And this has real implications in terms of showing trends for some of our internal products, right? Okay, so let's talk about the hybrid modes. This is slightly pretty new. It's not just running Pig on Storm. It is something more than that. So let's look into the motivation for this. So let's say you have a user event coming in. So let's say you have a user coming on your website, and you want to serve real-time content to that particular user, and personalized content, rather, right? So you would take that particular user event and look up the user profile into your offline system, which may be generating this user profile once in a while, let's say once in every 2 hours, because there's a lot of data which has to be crunched. And this profile gets generated, let's say in MR, right, MapReduce. Now, you look up this particular profile, you look up your content pool, you match the two, and then serve it in the fast path. So you see the top line actually shows the fast path, which is in Storm. And you also have the offline model, which is running in MR. Now, for each of these real-time user events, you also want that apart from serving it in the fast path, you actually persist that particular raw user event into the offline model for the MR to pick up in the next iteration for profile generation, right? So here you see there is interaction between both online offline systems, real-time and offline systems, Storm and MapReduce, and there is data exchange between two. There could be other use cases. For example, you may be getting data in real time, and you want to do some kind of aggregation and processing in that particular data, and that data is huge, so you do it in MR to get the right calculations. But you do not want to wait for all the calculations to finish, and what you want is, what you can do is you can process it in FastPath with very less data, and you can get some kind of an estimate, which is fine enough for now. And then later, you can always get the right data from the offline model whenever it finishes, right? So these are some of two of the motivations for this kind of an architecture. So conventionally, the way it is done is you create two pipelines, the FastPath processing pipeline using maybe Storm, and then slow path or offline processing pipeline using MapReduce. And then you write your data exchange mechanisms between the two using some kind of a state store like HBase or whatever. You write your own custom schemas, and then you write all kinds of logic to do read-write synchronization and whatever data exchange mechanism has to happen here. Now, we found this pattern to be very common in a lot of applications which we deal with, especially machine learning applications and stuff like that. So, and I mean, real-time applications where both these systems interact. And so we thought that it would be cool to actually capture it as a framework. And hybrid mode is that framework. So the value proposition for hybrid mode is that you write your pig script, and it will run, the parts of the script will run on Storm, and part of that will run in MapReduce, and the data exchange mechanisms between the two will happen automatically. You do not have to worry where what runs. You will get what you want, actually. And the data exchange happens at the granularity of a relation. So the earlier script which I was showing you looks like this in the hybrid mode. It's the same script. All I have done here is the text in red shows that I've increased the batches from 6 to 1,000 batches and decreased the frequency of crunching of these batches to like 10. So the way you read this is every 10th batch, read in a relative state of 1,000 batches with respect to the current batch. So whenever a system sees this, it sees that I have a lot of data to crunch because the range of the batches is like 1,000. And I have to crunch it at a very low frequency, so most probably this is like a perfect fit for doing it in MR. And from that statement onwards till the MR job boundary, it actually takes all these statements in blue and executes in MR. And all the rest of the statements execute in Storm. Now, for a user, it doesn't matter anyway because he's just dealing with one pig script. So large batch ranges, low frequency of processing, and high data payloads are some of the things which help decide what should run where, right? Those are some of the deciding criteria. Now, how do we figure out the boundary between these two jobs, Storm and MapReduce, and where do they merge? So whenever you're working on a relation, when you're doing any kind of a join operation between, or joint operation rather, between any of the relation, one coming from MR and one coming from Storm. So here in this case, Ngram model is coming from MR and Ngrams is coming from Storm. Whenever you're doing this kind of a join, you know that the data is merging at that point, and that forms the boundary between these two jobs, right? So that's how you figure out what should run where. And this is how the architecture for hybrid mode looks like. I'm not going to get into the details of this, but some of the key points here are that the same pipeline architecture which I was showing you earlier, this is more a generalization of that, so that you just submit your script and automatically you do not have to worry about what kind of schema or what kind of store you use. All this is set up for you automatically as part of the framework, right? And apart, if you are not interested in automatic division of jobs between Storm and MR, you can also decide and override and say which part should run on MR and which should run on Storm. So those things are possible. Now, the hybrid mode is something which we are coding right now, so it will still not available that way, but Pig on Storm is available and working right now. So next, we are working on performance testing at scale, installation, setup, demo, documentation, et cetera, and of course, coding hybrid mode. We're also working on state optimization. So state is a very important thing for us, and it comes up in every application that we deal with. So we're working on state optimizations, and if we are able to finish all this, we should be ready to kind of open source it if the community is interested. So we have not taken a call on that yet. So you can actually find out more details about this whole thing, about job creation and how does this whole thing work in the slides which will be online. I'm not going to get into the details. These are implementation details. And yeah, those are internals basically. And if you have any more questions, I can take it right now. Yes? So right now, actually, we just download the current version of Pig, and it works on that. So we actually, I have some, it's not in this particular slide. Yeah, so I don't know, it's not open source yet, so I mean, it doesn't matter really. It's all internal right now. So we just want to figure out, actually, after talking to folks here and maybe outside, that how many people are interested in this kind of project. what is the value gain that it provides. So, sorry, you had a question? Sorry. No, this doesn't assume that, but yeah, Storm could be on Yarn because that's just going to schedule Storm topologies on Yarn, right? So that's not a problem here at all. So actually, one of the other things, very interesting thing here is you can actually remove the MR paradigm with, let's say, Tez, because Pig is now available on Tez. So right now, you can actually have any paradigm. You can have Storm, you can have Tez, you can have MR. Wherever Pig works, this thing is going to work for your offline online systems, right? Sure. Okay, so that's pretty interesting. So there are two things actually. By default, we come up with a generic schema which is based on batches. The row keys would be batch IDs plus partition ID. This is something by default it is provided. And our UDFs, which we write for loading and storing data from HBase, work on this particular schema. And this is pretty generic schema actually. But if you want to override that, you can do that with your UDFs. The only thing is whatever you store and load should be, your UDF should understand this. So by default, we have a very simple schema where you have a batch ID and a partition ID. And partition ID actually corresponds to multiple tasks which run in Storm. So each of the tasks loads these parallelly, because in a batch processing mode in Storm, each of the tasks is processing the same batch all the time actually, right? Sorry. Oh, so actually, the way we use it right now, it is in memory and backed by, it can be backed by a store. So it actually depends on how much you can put in memory. But yes, if it blows up, then you can actually use any kind of a store or back it with a store. So sliding window does not assume that you need to actually have everything in memory only. You can actually have it on disk if you want, just that you will pay the price in terms of the disk IO. Sorry, I can't hear you. So right now it is not standardized that way, but we have implemented this for in-memory backed by HBase actually. So in case the main question comes here is if the sliding window goes down because the bolt went down, then how do you build it back? So that's the reason you back it with HBase, so that if it goes down, you reconstruct that sliding window again. So yeah, when we standardize on an API, then yes, those kind of things will come into picture, but it should be pluggable. Whatever store should be pluggable behind the API, so that the sliding window semantics still is an abstraction. Sorry. Right now, actually, we are running it together, but so that's more to do with HBase and HDFS, and I'm not the right person to talk about that, but that's a separate problem altogether. It's to do with how you run these two systems more efficiently, and that's used not just in Pig on Storm, it's used in a lot more applications. So I mean, there are better experts to talk about here about those, right? Okay, any more questions? So yeah, if you're interested in this, if you have any suggestions here, please talk to me. And this is my Twitter handle, or you can talk to me after this talk. And if you're interested that this makes sense for you, we can talk about it and develop new constructs. One of the things is here we are trying to enrich both Storm and Pig at the same time. All right. Thank you.